Concentrations. What is a concentration? Concentration is a measure of dissolved particles in a solution. Recall that a solution is a mixture of two or more pure substances, that is a homogeneous mixture. In a solution, we have two basic parts. We have a solute, which is the thing that is dissolved in solution, and a solvent, which is the thing that does the dissolving. If I take, for instance, sodium chloride, table salt, and dissolve it in water, the sodium chloride is the thing that is dissolved, so is the solute. The water does the dissolving, so is the solvent. A concentration, then, is a measure of the amount of dissolved solute in a solution. I generally express concentrations looking at a specific numeric value, and when I write those expressed concentrations, they are often expressed in brackets. Writing a bracket around a numeric concentration indicates that it is a measure of the concentration of that thing. So if I had a concentration of sodium chloride at 1.0 molar and I put 1.0 molar sodium chloride in brackets, that would be expressing that concentration. Looking at concentration, there are two basic types of concentration measurements that we deal with. We have mass measurements and mole measurements. Looking at concentration by mass focuses on the mass of the solute in a solution. And there are two different types of concentration by mass that we deal with. There is percent mass volume and percent mass mass. Percent mass volume expresses concentration as a percentage with the ratio of the mass of the solute to the volume of the solution. It uses measures of grams of solute and milliliters of solution. Looking at percent mass mass, the measurement is mass of solute per mass of solution. Both of them are in grams and expressed as a percentage. So as an example, a percent mass volume solution would be made if I had, for instance, 15.0 grams of glucose dissolved in 300 milliliters of solution. I would take the mass of the glucose, divide it by the volume of the solution, 15 divided by 300, express that as a percentage by multiplying by 100%, and in this case I would get a 5% solution mass volume. This is very common in medical instances. If I have a solution of saline or glucose and a saline drip, something like that, oftentimes is measured in mass volume. Often very common measurements of concentration by mass are things that are measured in mass mass. Things like the amount of a gas in a solution or amount of metal in a particular alloy are very common in mass mass solutions. For instance, if I took 10 grams of calcium gluconate and dissolved that in 100 grams of solution. Now, 100 grams of solution made from initially 10 grams of calcium gluconate, presuming that water is the other component to the solution as the solvent, the water would have to be added 90 grams to the 10 grams of calcium gluconate, which would give 100 grams of solution. In measuring then the mass percentage, we would take the mass of the gluconate and divide by the mass of the solution. So 10 grams of gluconate would be divided by 10 grams of gluconate plus 90 grams of water, which gives 100 grams of solution. And then the result is multiplied as a percentage, giving an overall 10% solution. Looking at percent mass mass, because of relative densities in various solutions, normally 100 milliliters of a solution is not 100 grams of that solution. For example, the density of the gluconate solution just mentioned is 1.07. So 1.07 grams per milliliter would give 107 grams in 100 milliliters, not 100 grams in 100 milliliters. Very commonly, we also find that when we combine things together, if I have a liter of solution of one type and a liter of solution of another type, I don't always get 2 liters of final solution. I may get less than that. And this happens with the way that things mix together. Adding the gluconate or the solute to the solution gives it a higher mass per volume ratio than the standard solvent would, so you wind up with a little bit more mass, and this is very common in solutions. Looking at other types of concentration by mass, we expressed our earlier mass in terms of a percentage. There are two other basic types of additional measurements we do with mass, and those are parts per thousand and parts per million. Looking at parts per thousand, which is both parts per thousand and parts per million are common in things like wastewater treatment and looking at contamination examples as units of measurement. If I had that previous example of the calcium gluconate solution dissolved in 100 grams of solution, if I express this as a parts per thousand or ppt solution, instead of multiplying by 100%, I multiply by 1000 ppt. So I take my 10 grams divided by the 100 grams of solution and multiply by 1000 ppt, which yields a 100 ppt solution. Doing the same for ppm, I would take my solution and multiply it by a million parts per million, 10 to the 6th. So if I look at the same solution, 10 grams of calcium gluconate and 100 grams of solution, when I do the division, I would multiply by a million, yielding 10,000 ppm as a solution. So I would have 10% as a percentage, 100 parts per thousand, and 10,000 parts per million. The other basic unit of concentration measurement that we deal with is concentration by moles. Concentration by moles is extremely useful for things like stoichiometry in solution phase. And there are two basic types of concentration by moles that we deal with. There is molarity, which is the most common, and expresses concentration in terms of moles of solute per liter of solution. And then there's molality, where molality expresses moles of solute per kilogram of solvent. It is the only one that we have talked about so far which has expressed the solution not in terms of a solution volume or solution mass. It's taken solute and solvent and compared them directly rather than comparing solute to solution. So if I look at an example of molarity, for instance, a molarity is abbreviated with a capital M, it's just italicized, and it stands for the unit molar. So if I talk about things in terms of molarity, I would say I had a 1 molar solution. If I took, for instance, 3 moles of sodium chloride and dissolved it in 2 liters of solution, I would take the number of moles, divide it by the number of liters, and get, in this case, a 1.5 molar solution of sodium chloride. Molality is abbreviated with a lowercase m that is italicized, and this is referred to as a molal solution. So if I had, for instance, 2 moles of sodium chloride and 3 kilograms of water, this would amount to taking the moles divided by kilograms, and I would get a 0.67 molal solution. If I'm looking at calculations using molarity, for instance, if I have a 96.4% sulfuric acid solution with a specific gravity of 1.84, what is the molarity of that solution? I can convert between percentages and molarities using some simple steps. If I have this, I'll take my specific gravity and express it as a density in terms of grams of solution per milliliter of solution. I can turn that from grams of solution into liters by multiplying by 1,000 milliliters per liter, and that gives me 1.84 times 10 to the 3rd grams of solution per liter. Next, I can figure out how much of that solution is sulfuric acid, and I know that in 96.4%, for every 100 grams of solution, I have 96.4 grams of sulfuric acid. So if I take 96.4 grams of sulfuric acid per 100 grams of solution and multiply it by 1.84 times 10 to the 3rd grams of solution per liter, I wind up with 1.77 times 10 to the 3rd grams of H2SO4 per liter. Now the obvious next step is to take grams of sulfuric acid and convert it to moles, which will give me a molar solution. So if I take those 1.77 times 10 to the 3rd grams and multiply by the molar mass at 1 mole of sulfuric acid per 98.1 grams of sulfuric acid, I wind up with an 18 mole per liter solution, or 18 molar solution.